going to go through assuring microliter volume handling and molecular analysis using dual dye ratiometric photometry. We're going to be discussing how to optimize your automated liquid handler for the best outcomes in your PCR-based assays with dual dye ratiometric photometry. First thing we need to look at when the most important factors to assure proper assay development and outcomes is to start with the liquid that you're using in the assay. Adjustments to your liquid handler are designed to increase accuracy and precision of liquid transfers and decrease variability of the assays and assay results and even false results. Therefore, the type of liquid you are working with will have an impact on the accuracy and precision of your liquid handler. Thusly, it's critical to accurately replicate the liquids when you're setting up your ALH. As you can see, these are just some of the attributes of fluids that can affect your deposition volumes in your ALH deposition. This next slide, the graphic on the left, shows what we like to call our dream ALH. Since there is no ALH out there that has this full array of settings, it's critical to get the liquid class equivalent and a precise measurement method such as dual dye ratiometry for your assay to assure microliter volume deposition. If you get the correct liquid mimic and optimize the ALH, you'll be able to increase your accuracy and precision, minimize your overall variability, and most importantly, improve patient outcomes. So this was a controlled assay where we altered the volume of the master mix used in your PCR assays and showed how that incorrect volume affects your CQ values. As you can see, the CQ values dramatically increased with the poor precision of deposition here. And the falsely high CQ values means improper gene quantification, of course. What I want to focus on here, too, is the required volume was 10 microliters. You can see even at 8 microliters here, although it doesn't look like a large-scale change in your CQ value, even that change in your CQ value is going to affect your assay outcomes because it's going to have a much greater effect on the assay outcome than the small change looks like there. So it's important to understand that delivering the correct quantity can translate into the possibility of misdiagnosing patients. In this particular slide, we're going to talk about what is master mix. It's a concentrated, complex solution of many components. Master mix reduces pipetting steps and therefore chances for error. However, it is also difficult to work with and has its own challenges. As you can see here, this is a automated liquid handler that we dispensed 4 different commercially available master mixes. And you can see our target was 10 microliters. Unfortunately, none of these actually delivered 10 microliters. This is an unoptimized liquid handler, by the way, before I start there. You can see master mix number 4 was close with the best variability, but even at that, if it only delivered 9 microliters, that would have effect on your assay and the outcomes of your assay. So it's important to make sure that you're going to optimize your assay, optimize your liquid handler to assure the proper deposition of your master mix in your solution. I changed those slides, so I'm going to jump back and forth here. So on this slide, we're talking about maximizing, again, or optimizing your liquid handler. In this particular case, we optimize the liquid handler using Artel's QualiSure PCR mix, which is a master mix liquid mimic. And you can see once optimized, we were able to deliver the 10 microliters with very good variability through the liquid handler. However, you can see when we tried to dispense an aqueous solution, we under-delivered by a substantial amount. This is important to understand because if you tried to optimize your liquid handler with an aqueous solution, you would not deliver the proper amounts of your master mix and therefore would overly affect your PCR assays and potentially your patient outcomes. Okay, so now I gotta go back. So just to quickly summarize why it's important to use a mimic for your master mix. The dispense step is a critical step in the process. If volumes are dispensed incorrectly, you can get false negatives, false positives, you're going to waste sample, and more importantly, you're going to get incorrect or inaccurate outcomes, which could affect patient diagnoses. Okay, so now we'll skip there. Okay, so some other sources of PCR variability are the ALH brand and model and platform. We already talked about the liquid class. We're going to talk about assay component volume variability, and then a little bit about training as well. So let's quickly talk about the ALH brand. If you have one ALH or liquid handler in your laboratory and you optimize it for your particular assay in your laboratory, and let's say everything's going well, and you want to move it on to the next stage or upscale or into the next phase of the process, and you have to move it to another ALH brand, it's important to understand that you're going to need to re-optimize that second ALH. Just because you've done it on one system doesn't mean it's going to be accurate on the next system. So using dual dye technology and a liquid class mimic, you're going to go back and re-optimize the new ALH so that you can deliver the correct volumes for your assays. Then we're going to quickly talk about component variability and some training here. So this slide simply demonstrates the importance of getting the DNA sample volume correct in a qPCR experiment, including even in NGS workflows. So if you highlight the 1 microliter volume here, which is where we were trying to target, and you look at 1.2 and 0.8, you can see that the 20% volume inaccuracy translates into roughly 20% concentration inaccuracy. If you're looking for a specific biomarker in this particular case, and the concentration is incorrect, then your biomarker quantification is also going to be incorrect. So it's important to understand just how critical it is to assure you're getting the 1 microliter and getting your assay correct, because a 20% inaccuracy volume is going to cause problems with your assay. So finally, we're going to look at a little bit of training here. This is one of my favorite slides because I really love the pre-training slide. It looks like a scatter plot more than a graph there. So we're looking now at the manual pipetting in the extraction step and the sample preparation step here. And what we're talking about is if you have analysts who are pipetting like this over here, and you try and move that extraction or sample prep step into an automated system, you're not going to get accurate results, or most of the time you're probably going to get failed results. So it's important to understand that not only is optimizing your liquid handler important, it's also important that your analysts have the capability to pipette accurately and precisely when moving it into your automated system. The dual dye technology, as well as optimizing your liquid handler, can also help you to train your analysts. So you can see here, after training, we have a nice cluster of data points there. And now once that extraction step is done with the manual pipetting, it'll move into the automated system, and it will give you accurate and repeatable results. Okay, so the dual dye ratiometric system that I'm talking about is done on the Artel by Advanced MVS system. But there's just a couple of other methods that are out there that potentially could be used. There's gravimetry. Gravimetry is very good at large volumes, that doesn't have the accuracy at low volumes because of the sensitivity to environmental factors. Fluorimetry and single dye photometry have good precision but limited accuracy because standard curves have to be set up for each individual process, liquid and assay. Dual dye technology has good precision at all volumes, as we've said, good accuracy, and it's insensitive to environmental factors, as well as it has the traceability that is needed for many of the applications, and the software handles all of the curves and everything for you. So how does dual dye technology work? It's really quite simple. Oops, doesn't look like that's working. Anyways, we shine a light. Oh, that's right, it's a PDF, it's not a slide. So we shine a light through a filter, which isn't shown here, through a blank vial, which has a dye in it. We have a detector, and then we measure the absorbance of that what we'll call a zero dye. Next, we add a second dye, a red dye, we mix it together, and then we put it back into the system. We shine a light through a second filter, through the mixed dye, a detector, we measure the absorbance of that. We calculate the difference between the two absorbance factors, and we measure out a precise and accurate volume deposition with the dual dye technology. So, in summary, dispensing of microliter volumes is challenging and has many variables. The liquid class, the volume deposition, and training all affect the assay's outcomes, and it's important to understand this. So dual dye ratiometric photometry technology optimizes and verifies all aspects of your liquid handler assays development using liquid class mimics and assured volume depositions. So that ends our session today, and I hope you gained some insight into how these technologies can help you.